Alright, in this part we will look at binomial formula, and that's something very interesting. Binomial formula, it's the generalization of the identity, the expansion for the square of the binomial, something like this expression. You knew this expression for a very long time. You might also knew the cubic version of this expansion or even the fourth power version of this expansion, but the binomial formula, that's the one which can give you the answer for any possible integral power n. This is this new symbol, like a flipped over letter, capital letter A. This is just the abbreviation which reads for any. So the binomial formula, it's a general formula which gives you the expansion for this for any integral n. There are two ways to write this, and the shortest, advanced way to write this is what is called sigma notation, and that's the expression like this. We'll get through this expression in a second. Just for now, just remember that this is what is called sigma notation. Sigma notation, and this symbol here is just the abbreviation for the expanded version for the expanded notation, and in the expanded notation you have something like this. The connection between this one and this one is very simple. All you do to to see the connection between this one, this notation, and this notation, or this writing, is just this. You take this expression which sits under the sigma symbol. By the way, I didn't mention that this symbol, it's a Greek letter sigma, and that's why we call it a sigma notation. So all you do, you take the expression which sits under this sigma symbol, and you make your index k here, index k, run, or in fact take, every integral value between 0 in the bottom, which is set here, and n at the top. And that's what I did here. For instance, this first term, that's the one which corresponds to k equals 0. Look at this carefully. K here is 0. When k here is 0, n, the a, this position will be a to the power n, b to the power k. The same story goes here. This is a term which corresponds to k equal 1. This is a term which corresponds to k equal 2. And all of the other terms, you can write them. In fact, I can do it. Let me just do it here. So all of the other terms, well, I put the dots to conceal most of them, but I give you the last three. This one will correspond to k equal n take 2. This corresponds to k equal n take 1, and the very last one corresponds to k equal n. Let me just shift it a little bit like this. Right, so that's the two versions of binomial expansion. One of them is written with sigma symbol, and the other one is really the expanded one, but there's no difference between them two. And I put both of them in front of you because sigma notation is something new to you, whereas the expanded one, something probably you more or less get used to. Now this C's, which you see here, this C's here, 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 these are something which is called binomial coefficients, and in fact there are a few ways how we can write this. There are a few notations for this one. The other one is this one, when you put two brackets around and put n over the k, but I personally prefer C because it's more console, like it's shorter, takes less space on a screen. But that's two identical notations. Both of them are quite legitimate, quite acceptable, and you can use both of them. Right. Now, the real question about the binomial formula, of course, is how to compute these coefficients, this binomial coefficient C. There are a few ways to compute these coefficients. The simplest, you might think, is a direct one. It's the one which is direct formula, which gives you the value of the binomial coefficient basing on the values of n and k. Let me just put it here for you. This formula, C and k, equal, it's a fraction which has n factorial at the numerator and k factorial times anti-k factorial in the denominator. This thing, let me use the other letter, m, with the exclamation point after it. This is the abbreviation for the product of all integral numbers from 1 up to the m. M here, of course, integral number. And the name for this thing is factorial. If you know it, it's good. If you don't, then that's all you basically need to know it. So if you go after binomial coefficient directly, that's the formula you should look at. That's the formula you should look at. However, it's not the best way to compute binomial coefficients, especially when you go after the coefficients for the lower values of n, for instance 2, 3, 4, 5, 6, 7, up to 15 in fact. That wouldn't be the best way to compute the binomial coefficients. The best way will be via so-called recursive relation. The recursive relation for the binomial coefficients, it's these three identities. First one says that the binomial coefficient with the index 0, it's always 1, which to us means that this coefficient is always 1. The second part of the binomial, of the recursive relation, is that the C and n is equal 1, which means that this coefficient is always 1. That's something quite expectable. Look at the initial at these two expansions here. Coefficients next to the highest power of A and highest power of B, they are 1s. Here the coefficient next to the highest power of A and the highest power of B is also 1. Now, the main substance of the recursive relation, of course, is this relation. This relation, which says that the binomial coefficient of the n expansion can be expressed as the combination of the binomial coefficients of the expansion of the n take 1. It's a very good relation. In fact, if somebody needs to compute a binomial coefficient, especially these days using the computer or any other like electronic means, that would be the best way to approach to finding binomial coefficients. Much better than, for instance, than the direct formula like this. However, for our purposes, this recursive relation, it takes the form of what is known as a Pascal triangle. Let me just put it here. Pascal triangle. And when you do this Pascal triangle, you do it like this. First, you start with the number 1. Then you put two numbers 1 and 1 underneath like this. Then you put another two numbers 1 and 1 underneath like this. Now let me move it over here. Pascal triangle. Recursive relation of Pascal triangle. And then the interesting thing is, now in this position, in between these two numbers, you put a number which is sum of the two numbers above it. So the number 2, that's the number which is a sum of 1 and 2. And that's how you build the third level of your Pascal triangle. Now when you go, second level, yeah, it's a second level because the levels normally in Pascal triangle, they index with n equals, the indexing starts with n equals 0. So that's the first level of Pascal triangle. And this is the third level of Pascal triangle. Sorry, second level of your Pascal triangle. Now when you go after the third level, again, you put the identities on the end sides of your level, and then you fill in the interior by taking again sums of the elements, two elements above it. So you take the sum sorry. You take the sum of these two elements, which is 3. You take the sum of these two elements, which is another 3. You can keep going like this as long as you wish. Normally, people are easily construct this triangle up to the level 15. Let's just go a little bit longer. So again, you see, I just put the identities on sides, and then every middle one is just the sum of the number above it. So for instance, 4, it's the sum of 1 and 3. 6 is the sum of 3 and 3. 4 is the sum of this one and this one. Very soon you will realize that the triangle in fact is symmetric. So all you have to do, you have to fill the triangle only up to the middle line. So for instance, here's the values up to the middle line in the level number 5. Here's the values up to the middle line in the level number 6. Let me open all of the other levels. I mean, all of the other levels I get prepared for you. Level 7, level 8, level 9. Levels on this side, of course, are filled by the symmetry. Levels on this side are filled by the symmetry. That's the idea of a Pascal triangle. And then your binomial coefficients, that's basically the numbers on the corresponding level. For instance, these are coefficients of the level 2. Look at the coefficients 1, 2, and 1. And look at the coefficients over here. 1, 2, and 1. Level 3, coefficients 1, 3, 3, 1. And that's what you see here, the coefficients here. 1, 3, 3, and 1. Same as in here. 1, 3, 3, and 1. Right. What I will do now, I'll just write down the expansion for the level 8, because I have another example which concerns level 8. So let's just look what happens, for instance, level 8. It's rather fast, so we can look at this. That's the level 8. The coefficients on the level 8, here they are. Here, all of them, coefficients of the level 8. So when I go after the binomial expansion of a plus b to the power 8, here's my expansion. Look at the coefficients. First coefficient 1, next one is 8, right from here. Next coefficient will be 28, here it is. 56 for the next one, here it is. Then goes 70, here it is. And then the rest is just the symmetry. So the rest is actually this here. The rest is just the symmetry. 50, again, back to 56, 28, 8, and 1. Pay attention that if you look closely at the powers, we write here, for instance, 6 and 2, or here 5 and 3, or here 4 and 4. If you look at these powers, you will realize every time the sum of them is 8. 6 plus 2, 6 plus 2, 8, 5 plus 3, 8, 4 plus 4, 8, 7 plus 1, 8. This is of course the reflection of the fact that here the powers n take k and k, when you sum them up, it will be just n. Right. In the end of this part of the lecture, we just do one example. That's an example which involves binomial computation and complex numbers at the same time. All I have to do now, I just have to take this binomial expansion and plug in the corresponding values a and b in here. This is very simple. Here's what the result was. What's the result? 1 goes for this value, for a to the power a. 8i is the next one. 28i squared plus and so on. That's the expansion. we'll do the computation. We'll compute this expression just in a second, but before we do that, I'll just because we have to deal with the powers of the imaginary unit now, I'll make this I'll make this quick note for you that actually the powers of imaginary unit, they possess this cyclicity property, meaning that, for instance, z square I square, we know it's -1. I cube is just I squared times another I, and that makes it -I. I to the power 4 is just I squared times another I squared, and each of them is -1, so the result is 1. Here it is. And when you look at the fifth power, you realize that you back to the I, back to this position here. I equal I, so I to the power 1 equal I. You back to this position. Just, oops. You back to this position. So the powers of the imaginary unit, they go with the cycle 4. Yeah. The proper mathematical form of this statement will be something like this. I to the power n equal to the I of the power r, where n and r are connected by this relation, and r is the remainder of n when you divide n by 4 partially. Now, when we know this, we can easily finish our computation. Here it is. First, we combine all of the terms in this expression which delivers a real part, and that will be 1 here, -28 in here, +17 here, and -28 in here again, because I to the 6, this is the same as I to the second, our second degree. It's just because of the cyclicity with the step 4, so it's -1 again. So it's -28 again, and I to the 8 is just another identity. Now, when you go for the imaginary part, we combine all of the i's with the odd degrees. The first one will be 8. Here it is. Second one will be -56. It's I cube, which is -I. Next one will be +56. It's I to the 5th. Here it is. It's I. And the last one will be -8 for this one. If you look at the imaginary part, you will realize that actually it is 0. So the whole result, just the real part, which if you do arithmetic, is 16. It's not really a coincidence that the result ended up to be pure real number, but the reasons for that we will see a little bit later.